Hi, we're Group 66, and today we invite you on a journey where sound becomes diagnosis. Our project, Neural Network-Based Detection of Respiratory Illnesses, explores how deep learning can transform simple breath sounds into powerful medical insights. Imagine this, you're a rural healthcare worker with no access to radiology, but you do have a smartphone and a stethoscope. Could deep learning bridge that diagnostic gap? That's our motivation. Respiratory disease are rampant, but expensive diagnostics create barriers. What if auscultation, the age-old art of listening to breath sounds, could be supercharged by neural networks? So here's the crux. Can we build a model that listens to lung sounds and predicts illnesses? But it should be with precision and confidence. Not just yes or no, but nuanced predictions, even for overlapping conditions like asthma and bronchitis. The challenge lies in spectral complexity, data imbalance, and clinical noise, but we embrace that head on. Our focus is diagnostic classification. We restrict our scope to the most common and clinically relevant respiratory conditions, but designing a system that's modular, interpretable, and ready for edge deployment. We're not building a black box, we're building a tool physicians can trust. Our dataset is the ICBHI 2017 Respiratory Sound Database. It has 920 sound files, 126 patients, and a wealth of metadata that includes age, sex, BMI, plus finely labeled crackles and wheezes. It's rare to get clinically grained sound data this rich, and we use every byte of it. We structure our inputs as long audio clips and patient demographics. The model outputs a predicted diagnosis, but also a probability distribution, because in medicine, certainty matters. A confident asthma diagnosis is very different from a 50-50 asthma bronchitis call. Our exploratory data analysis reveals two dominant age groups, children and the elderly. COPD is the most common asthma, the rarest. Gender imbalance is stark, 63% of them are male. These insights helped us tailor our pre-processing and evaluation strategy. Pre-processing is where the magic begins. We normalize, resample to 22.05 kHz, slice pure respiratory segments, extract features like MFCCs, chroma, and MEL spectrograms. Windowing helps break down each sound into manageable pieces. This pipeline isn't just robust, it's clinical grade. Class imbalance, the bane of machine learning. We fight it all in our fronts. Stratified splits, weighted loss, and balanced accuracy scoring. Plus, by oversampling windows, we give rare class samples more representation without synthetic data. Instead of throwing everything into one big CNN, we go modular. 3 parallel CNN branches, one each for MFCC, chroma, and MEL spec. Each specializes in distinct audio traits. MFCC nails spectral envelopes, chroma decodes tonality, and MEL spec captures broadband chaos. All three features behave like images. 2D matrices over time and frequency. CNNs thrive here. They learn localized filters. For example, one kernel might detect a wheeze across frequency bands. This transforms breath into image and image into diagnosis. While the fusion model is our hero, we also train each branch alone. Why? To understand the standalone strengths. Plus, solo models are lightweight, ideal for low power clinical deployments or mobile diagnostics. These act as our baseline models. Here's the full architecture. 3 CNN towers feed into a dense fusion layer. We concatenate their learned embeddings and pass it to a classifier head. This architecture is flexible, interpretable, and battle tested. Our training setup, it has an ADAM optimizer, early stopping, dynamic learning rate scheduling, and batch sizes of 32. We log everything to our tensor board, checkpoint our best models, and ensure repeatability. For ablations, we just tweak input shapes. Training remains consistent. Our evaluation strategy, we use stratified train test splits, early stopping, and comprehensive metrics such as precision, recall, F1 score per class. Macro and weighted averages expose bias, while global accuracy reflects the top line performing class. This is more than accuracy, it's about fairness. Our top line accuracy is 93%. We have a weighted F1 score of 0.93, but our macro F1 is 0.56. That gap is because of class imbalance. Asthma and LRTI are underrepresented. This shows an excellent performance in comparison to our baseline individual model performances. The fusion model outperforms all baselines. It's 5.6% more than MFCC. Why? It's because of complementarity. MFCC catches airway constriction, chroma adds tonal nuances, and MELSPEC catches broadband noise. Together, they form a diagnostic symphony. Safe, confident predictions, with fewer errors and better minority class recall. This isn't our first rodeo. As a team, we've worked on voice-based attendance, genre class recognition, and environmental audio detection. That experience, from MFCCs to resonates, shaped every decision here. We stand on the shoulder of giants. Our work builds upon clinical grade CNNs, hybrid resonant architectures, and advanced loss function for class imbalance, all rigorously cited and benchmarked. In conclusion, we set out with a simple problem statement to create a tool that diagnoses lung diseases using sound, and we achieved exactly that with an astounding 93% accuracy. We still see a humongous scope for this in the future to test it on more data, to improve our accuracy, and to create a tool that will soon be used in every lung diagnosis trial. Thank you.